Good afternoon. My name is Stecki. I'm going to be talking to you today about managing technical risk with a digital risk twin. I'm the CEO of PHM Technology. We're a company that's part owned by Siemens, and we are developing the safety and RAM solution for Siemens. Just to run you through what we're going to talk about today, first to define what technical risk is, then to look at how we analyze and understand that using RAMs, reliability, availability, maintainability, and safety. Talk about how we're going to, how we've made a digital risk twin that enables people to do RAMs more efficiently using a model-based approach. And then talk about how that digital risk twin feeds into the broader digital thread that Siemens provides. Then the benefits, the outcomes that you can achieve using the digital risk twin, and then finally how that looks in terms of the solution for Siemens and how that's available. So the first thing is to talk about what is technical risk. So essentially what we want to do is to understand what are the particular failures and hazards that present based on the design configuration of your system. It means that we need to understand how these failures are going to manifest, and when they manifest, what that means to the safe, efficient operation of your system, to make sure that we can identify all of the risks and then categorize them. Some things that can go wrong will have a serious impact, whether it be safety, economic, or operational. Some failures that you identify will not have as much impact. But the most important thing that we're looking to eliminate is the failures that are not identified during the design process. So you can see on the right here, non-critical identified, so risks that aren't important but you still need to document. Risks that are important, the critical identified, but this last category here, there's critical non-identified. And it's those failures that tend to cause the most amount of heartache in a system. If you don't have a ready mitigation for that unidentified risk, you then have to try and remediate that during operations, and that's typically much more expensive than if you had addressed it during the design phase. So what we want to do is understand the consequences of that risk. So technical risk is really going to look at impacting the way that your design process is being run. It leads into certification. A lot of the systems that we look at are mission and safety critical. So aircraft, defense platforms, oil and gas, mining, heavy industrial equipment. Things that if they fail will have a significant economic impact or potentially impact, for example, on military operations. If you need something to be available and it's not, that presents obviously problems. These risks are typically considered in terms of reliability, so how often these risks are expected to occur, when they're expected to occur, and if you don't understand the reliability of the system, it means that you'll have unplanned downtime, which obviously is much more expensive to address. Safety is an important consideration. If you aren't able to demonstrate appropriate mitigations for potential risks, you won't achieve the certification. So for example, in the aerospace and the automotive industry, if you don't have a clearly articulated mitigation process to identify that risk and remediate it as much as possible, you're not allowed to operate the system. And it means that all of these risks together typically impact what we call readiness, the availability, the operational availability of the system, and importantly, the cost of ownership. And what we're about is trying to find the most efficient way of identifying and mitigating that risk from the earliest stage of design. We want to move that process as far left so that you can influence the design and make sure that those risks are accounted for as early as possible. So RAMs is the discipline, as I mentioned before, reliability, availability, maintainability, and safety. And the process is always the same. It doesn't really matter what platform you're looking at, what type of system. There are important steps. So you'll have the requirements for the system, what it needs to be able to do. And then within the constraints of that design, you need to be able to identify that risk as early as possible. You need to understand that risk We talked before about the critical and non-critical risks and so on. You need to understand and interpret what that risk will mean. You then have to establish the appropriate mitigation for that. Now, that might be that you design it out of the system as much as possible. You might add a redundant system to make sure that if one fails, you can still operate the system. And where it's appropriate, particularly now with people moving towards autonomy and so on, you want to be able to put in place the right diagnostics, okay? And what we mean by that are the sensors that will allow you to capture the data off the system that enable you to distinguish what the health state of that equipment might be and what failures might be manifesting. So that's on the design side, and all of that work has to be done in order to achieve things like certification and to demonstrate to your customer base that the equipment will meet its intended purpose. As soon as you start to operate that equipment, you have the same steps that are required. You still need to identify, now, not the risk of that failure occurring, but the actual failure as it starts to manifest in the system. So we need to make sure that we can identify which specific failures or hazards are presenting when you operate the system. We need to report that accurately. It's not enough, for example, to say that I have a pump in the system and it's not working. We need to know in what way is that pump not working. So it's important to be able to accurately capture the data from the field from that pump and feed that back, because depending on the way the pump fails, there'll be different mitigations that are required. Once we've reported that, we can then go back and start to analyse whether that's the most appropriate mitigation most appropriate mitigation method for that potential failure, and then optimise our response. So there's a full feedback loop within the conditions in which you operate that system. The loading factors, the environmental environment in which you're operating, the mission, are you operating the system for 2 hours a day or for 8 hours a day? All of that information is going to feed into the best way to be able to address those failures now as they're presenting in the system. And you can see on the right there those questions that we want to answer. So in design, what can fail? What does it impact? Why or how can it fail? And when do we expect it to fail? Which means that we can put in place the right maintenance procedures, for example, the right periodicity of maintenance, when you have to do it. And then again, once we're in operation, are we still able to operate the system and achieve certain outcomes? Is it mission ready? What are the key degraders that are presenting in the system? We might have designed it and expected that certain types of failure might happen more than others, but what are the actual failures that are starting to present? What are the things that are degrading the operational availability of the system? And all of that has to be done in a way that we can ensure that we can operate the system efficiently as and when we need it. It's available when we need it. Okay, so how does that get done? What we've developed is a digital risk twin, which is essentially a model of the system that allows us to capture and understand the functions and the functional topology of the system. So we can start to interpret when we lose one potential function, how that's going to impact the rest of the system. And what that means is that for each of those potential risks of failure, that has to be considered in the context of what that specific design configuration might be. If you have different variants of a system, will they have different impacts? The mission profile, so the way we intend to operate the system. Are we operating in an environment? So we do a lot of work in defence. Defence platforms could be used, for example, in a desert environment, or they could be used in a tropical environment. And obviously the maintenance that's required for those will be different because of the different environmental factors that are accelerating particular failures. What's the requirement for operational availability? Do we need it to be running 24 hours a day, or do we need it to be running only 2 hours a day? Obviously, that's going to have an impact on how often we need to perform the maintenance and how reliable that maintenance procedure needs to be. And all of it always comes back to cost, okay? At the end of the day, cost is a key driver in all industries, including defence. It's not as important, but certainly with the commercial customers that we're talking to, they're always looking for ways that they can address and minimise that cost of ownership. And it becomes a differentiating feature when you're presenting to the market. The quality and the cost of ownership, the quality, how often the system will fail, its reliability, and the cost associated with that. How much maintenance do I need to do? So the digital risk twin allows us to then understand and capture those risks in a way that is consistent, transparent, and explainable and extensible. So as you develop the system, we have this model, sorry, disoriented, but you can see over here on the right. Basically what it's doing is it's capturing all of the functions, the energy, the material, and the data flow that's going through your system. Okay, that's what all of those different lines represent. And essentially, that the first piece of the maintenance-aware design and ecosystem is this functional model of the system. What it means is that we can understand if we lose any particular function, it will automatically identify what the impact of that will be on the overall system performance. Okay, once we have that, we can then look at what the physics of failure might be with that. So, understanding how pumps fail, understanding how valves or electronic systems might fail. All of these are considerations that need to be understood so that you can understand the potential operational impact of that risk of failure. Once we know what those failures are, we can then start to assess the criticality of those. So there's a number of techniques, and I don't know if the audience, people know what fault trees, FTAs, failure mode effects analysis, FMEAs, and in aircraft and some of the more complex systems, they do functional hazard assessments for functional safety and so on. So the tool is able to take that system model, take the data that's been input there in that system modeling process, and automatically produce for you all of these analyses. And it's really important that these analyses are automatically generated directly from the model. So instead of doing them separately, that's the current practice. People are using different tools and they're trying to conduct these analyses manually. Groups of people sitting around typing information into spreadsheets and so on. It's a very different approach. Instead, what we're doing here is using the model, taking the subject matter expertise that's associated with all of the different types of domains that might be involved, hydraulics, pneumatics, electrical, electronic, mechanical. All of that domain knowledge is captured inside that digital risk twin, and it's then converted into these safety or risk assessment artifacts that are typically used to substantiate the safety of the system and contribute to the certification, right? To demonstrate from a third-party perspective that the system is safe to operate. Once we know what all of those things are, the tool can then be used to start to assess what the reliability functions will be. So essentially what we're looking at there is if we want to make sure that the system's available 95% of the time, we can set that as a target for a requirement for the system, and then use that to calculate what would be the required reliability of any of the subsystems or assemblies or components or even parts that are required to meet that overall system availability. Reliability block diagrams, Markov analyses. There's a number of different techniques and methodologies that are used to calculate reliability. And the combination of that safety and risk assessment and that reliability analysis supports what we call a reliability-centered maintenance. So this is really using all of those attributes of the system that we've now defined to go through a formalized methodology and establish what the appropriate maintenance procedure might be, or if it might require a redesign to substantially reduce that risk. Once we've got all of that, the RCM will tell you whether it should be a scheduled replace, breakdown repair, or perhaps a condition-based maintenance. And everybody's trying to get to condition-based maintenance. One of the things about condition-based maintenance is that not all failures are applicable or suitable for condition-based maintenance. So the RCM process will help you identify which of those failures are suited to condition-based maintenance. And then the next piece, the PHM module, is unique. What it allows you to do is to take the configuration of the system, the understanding of those failures that are suitable for condition monitoring, and it will tell you what combination of sensors are required to be able to identify those failures as they're actually occurring in the system. Okay? It's a very different approach to a lot of what industry is trying to do at the moment, which is to take data off the system and then without the engineering context, try and understand and analyze to identify patterns. Those patterns are related to the data, but they're not necessarily aligned or associated with the engineering domain knowledge that's captured in these safety and reliability assessments. So the PHM module allows you to identify what combinations of sensors need to be on the system, different configurations of sensors, including the built-in tests, the control sensors and everything that might be there, and then run trade studies around whether it's more effective to have additional sensors to monitor that equipment or not. Okay, what that means, I talked about dependency mapping. What does that actually look like? So what you can see on the screen now is for this system, we're showing that there's a failure in the pump assembly on the far left, number one. And because there's that failure in the pump assembly, it's going to impact the ability of the filter to provide its intended function, which leads to the second filter having a problem, and so on and so forth. So that process of identifying what the downstream impacts of that failure will be is dependency mapping. And importantly, typically this process is done manually. Okay, so I keep trying to compare between the manual approach and a model-based approach. The key things here are that if you have a complex system where you have many different components and systems and assemblies, each of them can fail in different ways. How that system design, that configuration is going to impact these dependency maps is that if I don't understand what the downstream impacts will be, I'm not able to accurately assess what the appropriate mitigation should be. So the first thing is the tool will automatically map that dependency. It will also then start to include all of the other information that we have in the digital risk twin. So what's the functional impact is the first thing. The second thing is to look at what the criticality is of that expected failure, right? Then we want to look at the reliability. It might be a failure that can happen, and if it does, it's got significant consequences, but it's not expected to happen more than once every 10 years. Okay, so that's one thing. But if it's a potentially dangerous failure that can occur, which leads to the loss of system, and it's going to happen every 3 months, obviously we then need to start understanding, what mitigation we need to put in place every 2.5 months or 2 months to make sure that those failures won't present. And again, all of that information is in the context of the system context. I don't know if you can read all of the things that are there, but how we're using the system, the mission profile, where we're using the system, the environment. Are we operating in a dry environment, or do we have sea air? So there's moisture in the air and salt that's going to lead to more degradation and corrosion and so on. As well as the environment, it's the duty cycle. Okay, so how hard are we running this equipment? Is it always running at the same level, or do we have variable load factors? We need to understand how they might impact the occurrence and the severity of any failure that's going to present. And then finally, do the failures of these systems then present hazards to the operators of the system? Okay, so distinguishing between the components that are related and the physical failures, that component ceases to operate as intended, and the consequences of that as a hazard. Does that mean that the system, in an aircraft environment, if you lose certain systems, you might not have the ability to land, or there can be consequences for hazards that are quite significant, and all of that needs to be understood. The problem will be if you look at ships and aircraft and these complex types of systems, you potentially have tens or hundreds of thousands of these potential risks. And if you think about the fact that people are currently doing this manually, you can appreciate that A, it takes a lot of time, B, it's a subjective process if you're manually documenting this, trying to understand what the impact of any particular component's failure will be on every other component or system in the equipment. And because the way that the standards require you to report these, they'll typically capture, for example, the initiating event, the next event, and the end event. the end level effect. In the example above, you can see where I've highlighted that there's the local, the next, and the end effect. They're 3 data points. In this example, we have 9 steps in the process, okay? And it's those interim steps that are understood by the people that are actually generating these manual analyses, but they're not captured, okay? And it's very valuable information. The reason being that it's that full association that will substantiate the efficacy of the analysis, so how accurate it is. The second thing is that we can use that full chain, that dependency map, to describe what we call a failure syndrome, okay? And it's these syndromes of failure that are driving a lot of the analyses that are used to verify the safety of the equipment. Okay, just want to point out as well that I'm using different systems. So I think I showed an aircraft before and now it's a ship. From the perspective of a digital risk twin, it's independent of any particular industry domain, okay? What we're looking at is the way that the equipment will interact, not what that equipment necessarily is. That's that system context that comes around, but from our perspective, a pump can fail in certain ways. We can capture that in the model, and whenever that pump is then put into a design configuration, it will have the same physics of failure, it will have the same functional outputs, and it's those functional outputs and how they propagate that are important, these syndromes, dependency maps. And because we're talking about automation here, the level of effort goes into developing the model of the system, okay? But from the model, we can automatically generate these analyses. So you can see here examples of fault trees and FMEAs and reliability block diagrams and so on. For people that have done them, it'll make sense. I guess the thing here to take away is that there are a lot of different analyses that are all based on the same understanding of the system, okay? And importantly as well, what we do is we combine the different analyses from different groups. So in larger organizations for complex systems, what you might have is one discrete group that works only on the reliability, one that looks only at safety, one that's only got the responsibility for maintenance, one that might only have the responsibility for diagnostics. And increasingly there are data science teams that are associated with all of this. So, you know, what we need to do is make sure that the way that these outputs are generated is consistent, that it's explainable, so that you can interpret this information at a later stage, and that it's reusable as much as possible. Because this failure information and these associated syndromes and so on, I'm going to demonstrate how we can then use that for doing things like fault detection and isolation and so on. But all of this comes back to the digital risk twin and the ability to have a standardized nomenclature and taxonomy for functions, failures, and hazards, an automated process to be able to generate these particular analyses. And the really important thing we think that offers to the engineer in the organization is that they shift the way in which they're doing the work. So instead of spending a lot of time entering the data into different systems and trying to compare how that might look in other discrete systems that aren't integrated, the tool allows you to put all of that information into the model, and then instead of spending time to transcribe data, doing what engineers actually thought they would be doing when they studied engineering, understanding the context of the problem and making decisions about how that information should be used in the design and the support or sustainment of that system going forward. Okay, so how does this all fit into the broader digital thread that Siemens provides? You can see here we're talking about a thing called a RAMS digital backbone. So these are all of these different analyses. What we want to make sure is that we can combine them all. They can all be digitized, take it away from the manual approach, make it model-based, digitize it. The two analysis platforms that we have are focused either on the design or the operation. So on the design side, we have the maintenance-aware design environment, MADE, and that's the tool that I just showed you before. MODE is a platform that we're currently developing in conjunction with Siemens, which is going to allow us to do that second phase, to understand what failures are actually occurring in the system, and to make sure that we can capture the data accurately and feed it back in so that we can close the loop and inform the next design process, as well as the way in which we maintain the systems. Obviously, there are services that are related to that. The tools themselves don't require configuration. It's more in this sense, enablement is around training people to understand. Interestingly, the biggest challenge that we have is that a lot of these domains, safety, reliability, and maintenance, aren't used to a model-based approach. Okay, so typically a question we have to work with the customers is, who develops the model? Who owns the model? Is it the system engineer? Is it the diagnostics engineer? Is it the reliability people? So working with people to understand how you can implement and digitize your current processes using the technology. And we've spent the last couple of years working with Siemens to make sure that all the information that we have inside the digital risk twin can be shared with and through Teamcenter. So, the current state that we have now is that you can develop your system engineering model in one of the whatever the tool might be. We can then take that data into Teamcenter and then use it to start to auto-generate some of the models that we need to support the digital risk twin. So as much as possible, we're trying to increase the level of automation and integration so that we can focus on engineers doing analyzing what that information means rather than transcribing the information in the first place. And the mode piece, maintenance optimization and diagnostics, the important thing here is that everyone's trying to solve the problem at the moment with obviously as much digital data as they can collect from the system. We think it's really important that we're solving engineering problems rather than data science problems. Okay? And what that means is you have to have that engineering context. So the way that we describe that is to talk about causation-based AI. So the model that we create, the digital risk twin, is essentially a causation model. If we introduce any particular failure, how that develops, what it means, what the consequences might be, that captures the domain knowledge of the engineers as they're developing the system. We want to bring that knowledge into the way that AI can be applied for fault detection and isolation in the system. Okay? Because the key thing is always keep them available as increase and optimize operational availability. At the same time, how can we do that in the most cost-effective way? So the first product that we've developed is going to be syndrome diagnostics, which I'll show you, but this is a representation of the digital RAM's backbone. So you can see on the top left, I think I've got a pointer here, don't know. Top left, you can see there's a PLM. All right, that's where it all starts. That's where the requirements are. That's where the system engineering is being done. Information can be transferred from that into the MADE model, which provides that digital risk twin. That digital risk twin will automatically produce the safety, reliability, maintenance data and the analysis outputs that you require to substantiate that your design is going to be safe to operate and efficient. It also gives us the information about what we need for a digital diagnostic twin. Okay, what are the combinations of sensors that will allow us to discriminate between those different failures in the most cost-effective way? Because if you don't design those sensors into the system, you're not going to be able to collect the data that you need. And importantly, there are some problems that can't be solved purely by data science. If you don't see a failure, the data's not there to identify a pattern. So for safety and mission critical systems, what's really important is you can't afford to have failures. In recent years, there have been aircraft that have fallen out of the sky and killed several hundreds of people. It cost the company tens of billions of dollars. You can't afford to make those types of mistakes with safety and mission critical systems. So our approach gives you the ability to pre-identify what those patterns might be and make sure that you have the right sensors in place to give you the data to be able to identify those patterns as they're starting to manifest. Okay? Once we go into operations, there's two ways to get the data off the system. There's digital failure reporting and there's manual failure reporting. So the data off the sensors is important, but it's equally important to make sure that the data that's captured by your maintainers is accurate and consistent and aligns with the data that's being used to analyze the system in the first place. So, they're the areas that we're currently looking at. Syndrome diagnostics is the first product. I'll show you more in a moment. Down below, GRIT, guided reporting and inspection tool. We want to capture the gritty detail about what's going wrong with the system. We want to do it in a way that's aligned, as I said, with the way that we're describing these potential failures in the first place. And then from that, what it means is, certainly for high value assets, you can start to develop what we call a digital availability twin. So the risk twin looks at the configuration of the system from a class perspective. The availability twin says, if I have a fleet of 10 aircraft, each of them performs slightly differently. The failure rates for different systems on different aircraft is slightly different. So if they're high value assets, what it means is you can start to develop a unique digital risk twin that's associated with one specific tail number or pennant number or whatever the asset might be. And it allows you to then optimize the maintenance for that specific asset in the context of the way it's being used and where it's being used and all the other things that I described. So for us, the availability twin is really important, but in order to do that and then feed the loop or close the loop back into design, the information has to be captured in a way that it can be fed into something like the SLM piece, Service Lifecycle Management, and it has to be done in a way that allows you to rapidly, ideally autonomously, update the digital risk twin that you have. And of course, what that means is you can improve future designs and so on and so forth. I mentioned briefly, sorry, I should have clicked the button before. This is just showing the way the data transfers. I mentioned syndrome diagnostics. Essentially what we've got here is, on the left you can see the model, that's the digital risk twin. What it does is it identifies all those different patterns of behaviour that are associated with a particular failure. That generates what you can see, the model outputs. You can see those arrows that are going up and down. Essentially that's a syndrome of failure. What we're looking to do there is to capture all of those patterns so that we can later analyse whether they're going to occur in the system. The PHM module in MAID allows you to make sure that you have the right sensors, and then once you're in operations, simply what we're doing is we're looking at all the data that comes off the different sensors. We're synthesizing that to understand whether any of the patterns that we've identified in our safety analysis or our reliability calculations are associated with a particular pattern that's manifesting in the system during operation. So we're not looking at all the data and trying to find patterns. We're looking at all the data and looking to find specific patterns. And when we find them, we know that they relate to particular failures, we understand the context, and we understand the appropriate mitigation that needs to be performed. Once you've got that, you can use the information to feed into operations. If I've got a particular failure manifesting on a system, I might need to reduce the load, reduce the speed. I might need to abort the mission that I have. I might need to close the equipment, shut the equipment down in order to be able to perform certain maintenance. All of these decisions will depend on an accurate assessment of whether these failures are manifesting in the system at any particular time. So this is a platform now that we're currently trialling with some of the Siemens customers we work with, and we call that causation-based AI, as I said before. Using syndromes, the product's called Syndrome Diagnostics. It's just an example of how we can use the information that the risk twin provides to inform different ways of using AI. We want to make sure that the AI that we're supporting or we're developing is focused on, as I said before, solving engineering problems rather than solving data science problems. And what does that mean? So I've tried to put this here into three different levels. What does it mean to the people that are actually doing this at the analysis level? So here in the yellow, you can see that the automation makes it easier because of the model-based approach. It means that we should have less errors. There should be less gaps. If you don't identify a failure, you're not able to mitigate it. So it's really important that we have higher fidelity on the potential risks in the system, and ideally to do that as far left in the process so that we can actually influence the design rather than simply documenting some of the problems that might be there. It means that you can do these analyses obviously faster. It means that you can do the schedule for the design process can be compacted because often safety can be on the critical path. And it means that because we have these analyses based on a model, it's objective, repeatable, extensible, and traceable. Okay, really important. So what we want to make sure, what we've tried to make sure is that for the people that are actually doing this, it's easier for them to use this process. They get a better result and they're able to add their engineering domain knowledge. At the system level, what does that mean? So let's take it at a managerial level. It means that you've got a consistency in the process. So we can optimize the way that this work's being done, and we can make sure that all the information is being captured and reused in the design process going forward. So we can close that design loop. Third point for the managerial is, and it's happening in a lot of the defense companies, particularly in the US, there's what they call the silver tsunami. So there's a lot of people with a lot of domain knowledge and experience which are leaving the industry. The people that are coming in don't have as much of that information, but if we can capture that information in that digital risk twin, we're effectively digitizing it, which means that we can reuse it going forward. So we want to make sure that we can digitize that information. And from the corporate level, you know, from the executive level, if you will, it means that you can demonstrate how you're digitizing. You can get a tangible ROI from a digitization or a digital transformation process quickly. You know, this is something that you can demonstrate an ROI in 3 to 6 months. We think that's really important. Obviously, it means that you'll get a better quality product. That has implications for your customers and how you can sell and how you're perceived and how you price your products. And lastly, it means that if you've got automation and digitization, you're reducing the cost of actually developing the systems in the first place. So we think there are manifold benefits, and they can be described at different levels based on who's asking the question. Talking about questions, I'm not sure if this is the right forum, but I thought I'd ask if there were any questions, and if you don't have any, I've got some that I could ask myself. But is there anyone that had any particular questions that might be out? So. So it's meant to be for all systems. Again, it depends on the level of specificity that you want to get into in electronics. At the moment, we look at the system level, right? So when we model the system, it'll include software, electronics, electrical, mechanical. So we're looking at the entire system. Future state for us will be to get down. I mean, we have partners, people we work with in industry, that they focus on looking at the failure modes inside PCBs, for example, right? Sorry?
I want to go much deeper into this because I would be looking for the IEC 61508.
Right. Yep. I'm happy to talk to you about it afterwards. Yep. Are there any other questions? I'll answer these quickly. When should I adopt a digital RAMs approach? Ideally at the start of the program, but it can be done at any time. You get the most benefit if you do it at the start. Can I use this technique and this technology on legacy platforms? Yes, but it depends, and you know, we would talk to you about what the impact would be, whether you're spending, you know, what are you trying to achieve? If you're looking to optimize the maintenance, it might make sense. If this is a design that you're constantly iterating, again, it would make sense to implement. What's involved in setting up a digital risk twin? We're at a booth over there. If you want to come across, we have an example. We've created a model of a small fan, and we can show you that the engineer that was involved in that created the model. He'd never seen the fan before. Took him 3 hours to create the model, and we can show you what the artifacts will be that are produced. So obviously it's a piece of string question. If it's an aircraft that you're looking to model, it's going to take more than 3 hours. But it also is possible to focus on only creating models at the high level and putting detail into certain aspects of the system that you're having problems with. Do you have data? Yes, you do. A lot of it's the domain knowledge. A lot of the information could be stored in your PLM system. So, you know, that's why we've developed the ability to take the information from Teamcenter and be able to use that to auto-create models. So typically, yes, people do have the information that they need. Change management is obviously something that relates specifically to configuration management. But in this context, I think the other thing is, how do we get people to stop thinking about entering data into an Excel spreadsheet and instead creating a model? And I think it varies based on the digital maturity of every organisation. But I mean, everything is going digital. So the question is not whether you're going to go digital with this type of approach, it's when you're going to go digital. So, there are considerations about how quickly you want to move, what the current state of maturity might be, how disparate the information might be in different systems, but, it's achievable. Importantly, it feeds into the next thing, that if you digitize your RAM's data, you can potentially use it for other applications. And because of the data structure in the digital risk twin, which is formalized, it means that it's easy to reuse that data at a later stage. And the last question, is it possible to really digitize domain knowledge? The answer is yes. Obviously, it takes a little bit of effort. You'll never capture all of the understanding. I mean, we deal with engineers that can walk into a plant, and by walking in, they can smell that something's wrong with the system. They don't need sensors, they don't need anything else, they just need to listen to the way the system is working, and they can figure it out. It's hard to replicate that, but it is possible to capture a lot of the information and understanding about what those risks are, what they mean, and then start to codify and formalize and repeat the way that you mitigate them once you're in operations. And that's it. Thanks for making the time.